Right, so yes, first of all, thanks to organizers for organizing this event and giving me an opportunity to speak here. And thank you all for coming in the morning to attend this talk. So today I'll be talking about the abbreviating of the simulating structure formation in extended cosmologies. I'm Ashim Sen Gupta. I'm a postdoc at Bielefeld working with Cora. So first of all, what do I mean by this title? So on a literal level, it's just the concepts that I talk about there are many terms, many abbreviations. You might say that all of what I talk about is unified by large-scale structure, but it involves approximate methods like COLA, which you've already heard about this week, which depends on LBT, Lagrangian perturbation theory. I'm trying to test GR and lambda CDM, more abbreviations, etc. So many concepts, many abbreviations. But on the level of physics, what do I mean? So again, we've already heard this, that large-scale structure gives us an opportunity to give us complementary cosmological information to what is found through, say, using the CMB. And that gives us an opportunity to test for gravity, our understanding of dark energy, for instance, and also to test various dark matter models as well. But obtaining the late time matter density field, and of course going beyond that to get galaxy field, well, I shouldn't say fields anymore because there's some debate about whether a galaxy catalog is a field. Anyway, galaxy catalogs are fields, etc. Getting these at late times that are accurate on small scales is quite difficult. It's a computationally and temporally expensive exercise to do. So the objective of what I've been doing with my PhD and now in my postdoc as well is to try and abbreviate that process. Okay, so again, we already know now, if you didn't, or by now you know that you can speed up simulations through various approximate methods or methods that are informed by analytic information. So that's how you get to approaches like COLA, co-moving Lagrangian acceleration, or fast TM, or bullfrog, etc. And the thing I want to talk about is that you can extend these approaches to fields like modified gravity by adding, for instance, a fifth force to these setups. And that's how you can extend approaches that are otherwise formulated for Newtonian or general relativistic setups to modified gravity setups. And in my case, that culminated in the HiCola project of my PhD. And more recently with Cora, I've also been trying to work on this from the wave dark matter paradigm. But in the interest of time, I'll focus on the modified gravity aspects, and you can come talk to me about wave-like dark matter. So since I've mentioned modified gravity, perhaps I should spend a few words just explaining what that is, just in case anyone wants a refresher. So if we think of Lovelock's theorem, which tells us that a theory of gravity that is written in 4 dimensions using the metric and its derivatives and has second-order equations of motion, the only theory that satisfies that requirement is general relativity. So GR is a very unique theory in that regard, and this means it's actually quite easy to get to modified gravity. You simply relax one of these properties and immediately you have modified gravity. And so if you want to chart the space of modified gravity theories, you can do it in this way, according to Lovelock's theorem. So if I allow myself to have something other than the metric, I come down this branch of this diagram and I can have new fields, maybe a scalar field, and we get to the scalar tensor space of modified gravity theories, and you can keep doing this exercise. You can add even more complicated extra degrees of freedom. You can have non-local operators, you can have higher order equations, etc. But I'm going to be focused on the scalar tensor sector of this diagram. And I just want to make a point that don't be fooled by the fact that the scalar tensor space looks to be a small part of this slide. It hides more phenomenology than one may think. So for instance, DGP gravity and FFR gravity, which occupy the higher dimensional and higher order realms of this diagram, they can be reformulated as scalar tensor theories. So that's just one argument in favor of focusing on scalar tensor theories, not just because they're simple. That is admittedly one of the first reasons for doing it. It's simpler than some of the other parts of this diagram, but there's quite a lot of phenomenology here to study. So we'll be focused here, but it's not very small, and there's a lot that can happen in this. Okay, so I mentioned that my work in extending approximate rapid methods to modified gravity is culminated in the HiCola project. So what is that code for? Like, why did I develop that with my collaborators? So the context, of course, is that GR is a very successful theory. It's So it satisfies solar system constraints very well. The issue is that modified gravity theories with screening mechanisms do the same thing. So these screening mechanisms make them behave in the same way as GR does on these solar system scales. So these classical tests of gravity are not sufficient in differentiating between GR and modified gravity. And these screening mechanisms are typically nonlinear mechanisms. So if you do perturbation theory, you will not capture the behavior that comes from these properties. And so that's why we need to depend on in-body simulations to get predictions from these theories to then compare to, say, upcoming stage 4 survey data. And so that's the idea. That's why it makes sense to focus on methods that can rapidly forward model these modified gravity theories and give you the, say, large-scale structure information. And that's what the high color code that I've developed tries to do, and many other codes that have been developed since then try to do the same thing as well. We want to constrain theories with screening. That's the idea. Okay, let me now be a bit more specific about exactly which modified gravity theories I've been dealing with. So I've been working with reduced Horndeski theories. So these are theories that are basically described by this action. If any of you are familiar with Horndeski theories, essentially there's a missing term, a G5 term. This term controls how fast gravitational waves move, and because of GW17 at 17, it's usually convenient to satisfy that constraint by dropping G5. That is not the only way to satisfy the constraint, so I will just say that this is not the most general action you can write in scalar tensor space, but it's sufficient and quite generic. So, just to give an overview, this might look familiar to some of you. This is basically the Einstein-Hilbert term, but it just has a new coefficient that is now a function of the new scalar degree of freedom, phi. You can have a kinetic term for your scalar field, of course, but it doesn't need to be canonical. So it's not just d mu phi divided by 2, but you can have powers of that. So you can have non-standard kinetic terms. And this is an interaction term. And this is often the stuff that we're interested in from a screening perspective. This is where you can get, for instance, Weinstein screening from. And this is the kind of term that you would lose if you just did, say, linear perturbation theory or next to leading order perturbation theory. So the idea behind the high color code was to address this entire theory space as much as possible. So initially, high color was designed to apply to all theories described by that action with Weinstein screening, a particular kind of screening, a particular kind of behavior coming from this term. And since then, I then extended the scope even further to other theories, but I won't dwell on that too long, at least. Okay, so main idea. You can incorporate modified gravity into your n-body setups or your Kohler setups through a fifth force. So how do you get it? If you use the quasi-static approximation and you assume during the calculation that you make in perturbation theory that your matter is spherically distributed, and you make a quasi-linear treatment, so you treat your metric perturbations as linear, but your scalar field perturbations you keep non-linear, and you keep next to leading order, then you can write down a force of this form. And this is the total force. So this is the Newtonian, the GR part that you would expect, and also what comes from your new scalar degree of freedom. And what's key here is that none of these terms, so these new terms, do not depend on the scalar field perturbation. You do not need to solve the Klein-Gordon equation to get the total force. That's the main thing. That's the primary reason why simulating modified gravity is a difficult endeavor, because as it is, solving the Poisson equation is hard enough for GR simulations, and modified gravity comes with the added complication of a new equation of motion that can be non-linear, and that just is slower to solve. We can avoid that if we make these approximations. You'll notice that there are stars, of course, so these come at a cost, right? Like if you do this, you'll need to typically introduce a calibration parameter, so that's one shortcoming there. And if you do this, this is not always guaranteed in every modified gravity theory, so you actually want to check your scalar sound speed. But if you can mitigate these things, then this is not a bad approach. Okay, now let's say I make a particular choice for, because I told you about reduced Horndeski theories. That's still a space of theories. There are many theories that live in that subspace. Let's say I make the following choice. I set my Horndeski functions in this way, and x is simply the canonical kinetic term. So this is d mu phi divided by 2, or phi dot squared over 2 if you stay in the background, in the cosmological background. I don't want to claim that the cubic Galilean is a candidate theory for a universe. It's not. It's been ruled out, but it's a useful test case and has useful properties. So just roll with me for now. Now that I've made the choice, perhaps I can convince you that this particular form for the fifth force and these new terms beta and s have the correct behavior that we expect. So beta, which I call the coupling, that controls how strong the fifth force can be at any given time. And so what you see here is that if you go to high redshift, early times, beta is very small. So this is giving us the kind of behavior we want. If the scalar field is to act like dark energy, then at early times it should be relatively insignificant. At late times, when dark energy becomes a significant portion of the matter content, energy content of our universe, that's when it should be significant, and that's where you can see beta becomes close to 1. So this means that the fifth force is allowed to be strong. S is called a screening factor, as you might have predicted. This thing depends on density, and if I increase the density, you see I go down from these dashed lines to the dotted lines. So it basically kills off the contribution, the fifth force contribution coming in my total force, and I get back just the Newtonian force. So it's doing exactly what it says. If you're in a high density environment, the screening mechanism kicks in and kills off your fifth force. Right, okay, so I've now incorporated reduced Horndeski theories in a Kohler formalism. I can forward model this now, and I can generate particle snapshots. I have particle positions and velocities, and now I can try and study their clustering behavior. Now, some of you may be disappointed by this because I'm looking at ratios of power spectra, and that's kind of the point. I've been focused so far on power spectra, and you can see there's quite a lot to learn here, of course. So this is the ratio of the cubic LM power spectra divided by what you get from GR with the same initial conditions, etc., and the same cosmological parameters. So on the large scales, there's a scale-independent enhancement. That's what you expect. The growth factor term only depends on time, not on scale. Then as you go to smaller scales, you get scale-dependent changes. And finally, the enhancement with respect to GR is killed off on small scales. That's screening coming into action. So you can see that what we've encoded does include screening as we wanted, but as you may be able to predict, that doesn't really look like a very like a smoking gun of cubic Galilean. It definitely tells you don't have GR, so you might be able to say that I don't have GR when I get some kind of spectrum like this, if you can identify it. But how do you identify the cubic Galilean specifically from, say, galaxy survey measurements? That's an open question for me, at least. Okay, so I've showed you the cubic Galilean. Let me now just move on to another theory just to show you that you can do it for other theories. I've said it was generic, this code. This was there independently, so I didn't have this because of single meaning, but I'm quite glad that it was there coincidentally. There are another Tolkien references in there. But this is for camouflage gravity, or camouflage, I suppose I should say. I'm skipping over details for how this is implemented because this comes with the added complication of Jordan and Einstein frames. You can ask me about that if you want, but it's a different theory. It has a different functional dependence on X, and the scalar field is now affecting, you can't see it here because this is a different frame, but it's now affecting the coefficient of the Ricci scalar in the Jordan frame. The main thing I want to stress here is that just focus on the blue lines. The other lines you can ask me about if you're interested, because they just tell you exactly why you have this shape, but focus on the blue line. This is the full ratio of the power spectrum, the 2-point matter power spectrum. So you can see that the shapes coming from the cubic Galilean that you saw earlier and now camouflage gravity, they look similar. And especially if you cut yourself off at k of 1, it might become apparent that you might be concerned that there's not a great way to distinguish between the cubic Galilean and camouflage at this level, especially if you have the parameter dependence. If you allow yourself to freely vary this k0 here, this n over there, this beta k there, then there's no guarantee that this is not degenerate with, say, cubic Galilean parameters as well. So I think there's clearly a need to go beyond the 2-point. Now, I've used this to validate high Kohler, for instance. So I checked with cosmog, and that's how we get up to just over 1% precision, up to k of 1 with n-body codes. But if we want to learn how to distinguish between modified gravity theories, we need to go beyond that. Now, we might, for instance, do this by considering statistics beyond the 2 points. So let's say the 1-point statistic. I won't focus on this too much because Cora's already going to talk about it in more precision than me. But here I've picked 3 theories. You've already seen the cubic Galilean. ESSC is a model I haven't described to you, but just believe me, it's a pretty strong, it has pretty strong deviations from GR at the 2-point level. And then black is GR lambda CDM. Now, the question is, how can we use this in conjunction, say, with two-point statistics to identify specific theories and distinguish between them? So perhaps one way to go forward is to use density split statistics. There's been some growing development there, so check out this reference if you want to learn more. But there is hope that if we use these statistics, we might be able to figure out exactly where certain classes of reduced Horndeski models behave differently from GR and then identify between them. So that's just going beyond 2-point, but of course, the idea, I guess, in this workshop is to go straight to the field level. So I would love to discuss that. Like, how can we extract at the field level information that would distinguish? Okay, so let me just summarize what I've talked about. So you can make simulating modified gravity feasible if you adopt COLA. So COLA was described, I didn't really talk about it too much, but COLA allows you to cut the number of time steps. If you adopt COLA and you also use an approximate fifth force, then you can avoid the Klein-Gordon equation. So if you do these two approximations together, you make simulating modified gravity much more feasible. And so I just made the high COLA code for that, which will enable simulating a wide class of Horndeski model. So it's written with a symbolic manipulation module. So you can write down your favorite Horndeski model, and then it will attempt to solve it. So this code exists to do it for wide class models. COLA has been already used to make weak lensing maps for modified gravity as well. So it's not just galaxy clustering or data that you can generate there. You can do weak lensing maps, and this is pretty impressive. The accuracy you can get with respect to n-body codes is quite impressive. So check out that. And of course, the obvious future work is to go beyond 2-point, possibly up to the field level, to try and get distinguishing features of these modified gravity models. And of course, recently what I've been doing is taking inspiration from these particulate approaches to apply it to other dark matter paradigms like wave-like DM. And you can flip this thing on its head. You can, instead of doing this, you can say that you're going to model your particulate dark matter using waves. And this might avoid the problem of undersampling voids that happens when you use particulate dark matter. I'm just going to flip the point around so you can read it. So yeah, that's it. I'm done.